I am Hakeem Oluseyi. I am an astrophysicist and author of the new book, Why Do We Exist? The 9 Realms of the Universe That Make You Possible. Today on Big Think, we're going to discuss 3 of these realms: the quantum realm, the cosmological realm, and the multiverse realm.
Chapter 1. The Strange World of Quantum Physics.
Quantum physics is weird because it breaks every intuition of the physics that we normally experience in our regular world. The rules break. Certainty breaks. Things become probabilistic. Things come into existence, out of existence. Objects pass through walls. It is strange. How should we think about quantum particles? They are not things. They are not things like the world around us. Quantum particles are the fundamental constituents of matter that come together to build up the world around us. So protons and neutrons are made up of fundamental quantum particles called quarks. Light is made up of fundamental quantum particles called photons. Electrons are a fundamental quantum particle. And so they come together in ways that cause new properties to emerge that give us a reality that is fundamentally different from the reality that created them. When we look at an artist's description of what an atom is, you typically see something that looks like a solar system in 3 dimensions, right? You have these lines of electrons orbiting a nucleus, but that is not what's happening, right? Planets that are orbiting the sun, they're basically falling around the sun, just like an object falls here in Earth's atmosphere. It's the same process. Electrons are not falling around the nucleus of the atom. And the other thing is that they're not these little tiny spheres that we imagine. When you look at them at their fundamental basis, they have a particular property. And that is that every electron is identical. For example, you can't tell one from the other. So what that tells me is that gives us a hint of what they are. So I like to make the analogy that they're kind of like musical notes. If I hear a musical note, a C, every C is a C. They're identical, but is the C a real thing? What the real thing is the instrument or the voice that vibrated and created this vibration in the air. That vibration in the air is a real thing, but that perception of the C is, comes out of that vibration. And so how do you create a vibration? You add energy to the string or to the instrument that you're blowing. Well, reality does the same thing. At the most foundational level, there is this concept of quantum fields. And these quantum fields permeate all of space-time. And what we call a particle is energy injected into one of those quantum fields. We call electrons excitations in the quantum electron field. And, so in essence, we are a symphony of musical notes in quantum fields. And what's really interesting is that if you take that analogy to its extremes, right? If I have a musical instrument like a guitar that has a string that vibrates, if I don't pluck the string isn't vibrating, right? Well, not right. It turns out that if I zoom in and look at that string really closely, you'll see that it's always vibrating. And in the same way, those quantum fields are always fluctuating. And that means that there's 2 types of vibrations. The ones where you insert energy and get an excitation that results in a note, but then it still vibrates at the same frequency, but really tiny. Those are what we call virtual particles in quantum mechanics. So they both can exist on these quantum fields. So the thing about quantum fields that makes them really uncomfortable for me, and I thought, maybe this is just a mathematical analogy, is that they don't have some source like a magnetic field. You think, oh, here's a star, here's a planet. That's the source of the field. If you have an electric field, you think, oh, here's an amount of electric charge. That electric charge creates that electric field. And, most of the fields that we're normally concerned with, electric, magnetic, gravity, they're associated with matter. These quantum fields have no source. They're not necessarily associated with matter in the same way as far as they generate, some matter with some property generates a quantum field. They just seem to be there, just exist throughout all space, right? And so I thought I'm like, man, this just can't be real. This just can't be. And then in 2012, we discover the Higgs field, this scalar field that permeates all space and imbues mass to these quantum particles. And at that point, it's undeniable now. The quantum fields are real. And they are, the word field in physics means something really simple. It just means it has a value everywhere, right? So if I have an electric field, for example, I can characterize it by the strength of the magnet and direction of that electric field everywhere in the room. And if I put an electric charge in the room, that charge is going to feel a force from that force field that we call an electric field. So it's a real thing. And when we do physics calculations, like when we do quantum mechanics calculations, or, we use this word all the time, potential energy. Potential energy, what does that mean? Well, here's the thing. A field has different values at different locations in space. So potential energy is an energy that's associated with where you're located, right? Which is different from kinetic energy that has to do with how you're moving, right? How fast you're moving, how much mass you have, or collectively how much momentum you have. So quantum fields appear to be actual, real physical entities that are just there and are everywhere. So how do you think of these particles? Man, physicists have been asking that question since we discovered them. Sometimes they're particles, sometimes they're a wave. But when it comes down to it, humans ask these questions of what things are because we want to make a calculation to get something understood or accomplished. And based on what you're trying to accomplish, that's how you model it. So sometimes you model it as a wave. Sometimes you model the atom as an electron and a nucleus connected by a spring. Sometimes you do think of it as a little sphere. Sometimes you think of it as spread out throughout an entire material. And each time you make a calculation, you get the right answer using the physics of quantum mechanics. So what is it really? We don't know. What is a wave function? The wave function is a mathematical description of a quantum entity. And it lives in this funky mathematical space, this funky vector space. And so at the basic level, we make measurements of things. Where is it located? How fast is it moving? And this wave function, even though it does not have the same sort of tangible reality that we're accustomed to in classical mechanics, it gives us the right answers to the measurements that we make with incredibly high precision. So it is an incredibly valuable tool, but it has very little intuitive basis for a human that lives outside of the quantum realm. The big problem with quantum mechanics and translating it to others is that it's made up of, it exists in this funky mathematics that will make your eyes glaze over. And that is these vector math, right? So a lot of us have encountered vectors. So the typical place that we do is, you have your XY plane, you have some arrow that is a vector, and you can draw a line straight down to the x-axis and say, oh, here's where it intersects that axis at 3. And here's where it intersects the y-axis. And I can say that value is 4, for example. So I could write that vector as 3x plus 4y, all right? Well, when we describe quantum entities, we use this idea called a wave function. And the wave function is a vector in very much the same way. But instead of having an x-axis and a y-axis, you have axes that are physical observables, locations, momenta, energies, these sorts of things. And what happens is that when you write down that wave function, if you have 3x and 4y, what you know is if I make a measurement of that system, I'm going to get either 3 for x or 4 for y. That's the only possibilities. But before I make a measurement, the state of the system is a combination of 3x and 4y, right? So it's that vector sitting there at some angle. But now I make a measurement and boom, it's only on 3. Or boom, it's only on 4. But the analogy that I'm making is not accurate because my hand moved from the original vector space, that's a combination of x and y, to being either all x or all y, right? It rotated. That's not what happens. It appears to happen in the quantum world. It's like it disappears from being x and y and becomes all x. Or it disappears from a combination of x and y and becomes all y. And what's really freaky about that is that when you write down this wave function, let's say, for example, 5 different locations, all right? Every possible location is going to have a probability assigned to it. And so if it's 5 different locations, then you can imagine there's 5 axes. And so instead of just a 2D XY, imagine XYZ. And you have that vector sitting out somewhere in this space, right? Of this XYZ space. And when I make a measurement, it pops to one of those axes. When I start making measurements of what is the value of this thing when I measure it, I get this value of X, I get this value of Y, I get this value of Z. Each value is going to occur at the probability that that initial state predicts. But you can never know before you make the measurement which one you're going to get, right? So let me make a similar analogy. When we model, as physicists, a block of iron, right? Every atom is in a particular location. We call it a lattice, all right? And when you write down those lattice locations, they play an important role in calculations of what happens in reality. But if you were to actually look at those atoms, each little atom has a range of motion. That lattice location is going to be where it is located the least amount of time. It's not where it's at, it's where it's almost is never located. Here's another analogy. Suppose I have a pendulum, right? Suppose I have a series of pendulums, and I want to say where each pendulum is. If I don't energize them by lifting the arm and letting it swing, the best thing to say is that wherever it hangs straight down in that equilibrium position, that's where it is, right? That's where that pendulum is located. But now if I lift that arm and let it swing, what you're going to see is for the range of motion of that pendulum, that's where it's going to be located the least amount of time, right? It's going to go here and slow down, and it's going to speed through the bottom and go back up there and slow down. So it's going to be at its extremes way more often than it is right here, but that location is what takes place. That's what shows up in the equations. So are these quantum state vectors, these wave functions, the same thing, right? Is it that that vector is moving around that space at all times, and what we call the state vector is just the average location where it is, or way to characterize that vector, even though it's constantly moving around? The problem is we have no idea. That's the problem. And not only that, when I talked about a pendulum, we're talking about locations in space, angles, speeds, stuff that makes sense. The vectors in which these quantum wave functions live are this crazy thing called a Hilbert vector space, right? That has no physical manifestation in our regular world. So when we talk about how we describe the world with physics, typically it's an equation that says a physical thing changes with time based on the circumstances it's in. And those circumstances are either circumstances of energy or circumstances of force. For the Schrodinger equation and the wave function, the thing that changes with time is some vector in some weird Hilbert space. But from that, you get out what you would actually measure if you made a measurement with a higher precision than any other science. Do quantum fields exist in space-time, or does space-time emerge out of quantum fields? Space-time is kind of the combination of everywhere and every when in the universe. And, the wheres and the whens exist separately, but they also exist in a combination of a phenomenon that we call space-time, where it's expressed by a mathematical equation that includes, distance, it includes time, and it includes the curvature of space-time, as well as the change in the space-time coordinates with time, right? We call that a metric. So it's essentially a way of how do you measure distances in the universe? You use this notion known as space-time. Are our descriptions of reality, are they really representative of the underlying reality? Or are they tools that give us what's going to happen in certain situations? If space-time is a quantum field, then you should be able to quantize it, and physicists have been attempting to do that, come up with a quantum theory for space-time, and we haven't been able to so far, especially in high energy regimes. So, it's a situation where it's more like a superimposition, right? So all these quantum fields exist in the same space at the same time, right? So if you think of a mesh, one way I like to imagine it is take a swimming pool and fill it up with green jello, but also fill it up with red jello and blue jello and yellow jello and purple jello all at the same time, right? All of these different jellos are there filling the same space. Some of them interact with each other, some of them don't interact with each other, but they coexist throughout this space. And so, you would think that they are existing in a space-time, right? And, when we get to the multiverse realm, you'll see that space-time exists in a space-time, right? So reality is multi-layered, and quantum fields appear to be fundamental. Space-time appears to be fundamental. Some argue that space-time is emergent. I argue that space-time is fundamental because, again, fields, if they are fundamental, which seems to be the case, they require a geometry in which to exist. That geometry is space. Energy appears to be fundamental. Energy is that which creates change. For change to exist, there needs to be a before and an after. So time must exist. So space and time must exist for quantum fields and energy to exist. So is it that they come into existence simultaneously? It's kind of like supermassive black holes and galaxies. We see that they're both necessary and they're both there, and we can't tell which one came first, which is the chicken and which is the egg, right? It's that kind of problem. Can I explain entanglement to you? Well, thank you for your confidence in me. Quantum entanglement is a phenomenon that occurs in quantum mechanics when two or more entities behave as if they are a single entity. And there are rules that these entities must follow if they are a single entity. And the general statement is that they must be in complementary states. This is one of those things where, among physicists, a lot of us are convinced, oh, there is no mystery here. It's just a correlation. And we see correlations around us all the time, right? And then others are like, oh, no, 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 no. There's something really weird going on here. I'm a fence sitter in this argument, right? Because it is a correlation. But the thing that makes it really weird and strange is that you can measure these correlations. And so the analogy I normally give is, take a pair of twins, and they are correlated in the sense that when one is sitting and the other is always standing. And, you separate them by light years, take them to opposite sides of the universe, and give each one a set of scribes that records every time each one is sitting and standing. What you will find is that, years later, when the scribes from opposite sides of the universe come together and compare their notes, they'll see that the correlation held. And there was no way for them to actually have a signal go from one to the other in that instantaneous amount of time. But there's a big problem with that. And that is that it kind of rests on making measurements at around the same time. And so what is the same time? Well, that goes into the definition of what does it mean to have now, right? And so we define now as a set of simultaneous events that are occurring, right? That is what defines now. All these things are happening at the same time. Well, Albert Einstein showed us that events that are simultaneous to one observer are not simultaneous to another observer if they're moving differently and if they're in a different state of gravitational energy, right? And then, that was expanded to something called the Andromeda paradox that shows that this effect compounds over distance. So different observers looking at things in the great, very distance, right? Like say our two twins separated by some great distance, whereas one may see events as occurring as simultaneous, the other may see those same two events separated by days or years or centuries if the distances are great enough. So observation breaks down at great distances. So yeah, we've measured quantum entanglement across, distances that are great, like from the surface of Earth to a satellite, but we haven't done it across these super vast distances in which the universe actually exists. So, it's weird, it's strange. What is it really, the underlying reality? We haven't figured that out. Some folks convinced they have, and there's a big paradox there. I sit in the ignorance. I sit in the mystery, in the question, and in the curiosity. When I talk about the quantum realm, I'm sure your mind goes to, some YouTube video you've watched or some movie you've watched, Ant-Man going into the quantum realm, right? When we hear new information, we try to understand it through analogies or relating it to things that we already know. But there's nothing that we already know that is like the quantum realm. So as your brain tries to make sense of it, it actually confuses you more. You kind of have to empty your brain, throw it away, and build this whole new reality from the ground up in this strange math, right? And so that makes it opaque to most of us. Even us physicists, when we get into the math, again, we live in a world that makes sense to us. The quantum realm does not. So you're not alone if you have no idea what this is about.
Chapter 2, the cosmological realm.
When you think of the cosmological realm, think of dynamic space-time. And those dynamics manifest in two ways: space-time curvature and space-time motion, primarily stretching and waving. So the realm of cosmology is the realm of dynamic space-time. When I was a graduate student, my PhD advisor turns to me, he goes, "Hey, Hakeem, the solar radiance is like, something, 10 to the 30 ergs per second or some number 10 to the 30th. And I go, yeah, I don't know. And he looks at me and he goes, "What? You call yourself a solar physicist and you don't know the solar irradiance?" Right? With this look of almost disgust. And I was like, yo, Hakeem, bro, you need to step up your game. You need to get these numbers embedded in your head. And so I started to understand reality at the astronomical scale in terms of these numbers. I came to understand, like, hey, the moon is 1% the Earth's mass, but 1/4 the Earth's diameter. Mars is 10% the Earth's mass, but 1/2 the Earth's diameter. The sun is 100 times the Earth's diameter. And as I had these numbers in my mind, I was going about my business of being a student, and I taught observational astronomy at the observatory. And one night I was leaving the observatory very late at night, 4 a.m. or so, and it was a clear night, and I looked at the moon. And I contemplated on the fact that the moon was 1/4 the Earth's size. And the fact that it is around just over 60 Earth radii away from us, right? So if you ask a person, if this is the size of the Earth, how big is the moon and how far away it is? You get something like this, right? But it's really 60 some odd Earth radii away. So 60 times that distance away is on the other side of the wall over here, right? And so when I realized that the thing was 60 some odd Earth radii away from me, and I saw how big it was in the sky, I could suddenly see the sky in 3D. Also in the night sky was Jupiter, and I knew it was on the opposite side of the sun and it's 10 times bigger than Earth. And seeing how big it appeared in my night sky, knowing these distances, right? Things look smaller the farther away they are. Knowing these distances, I was like, holy, whoa, how massive and large Jupiter is, right? But then one night, I had this buddy who he had not done well in school. Let's just say it that way. He wasn't an academic dude, but he had crazy curiosity. And one day, he invites me up to his father's home in the coastal mountains of California outside the town of Elk. And he's like, "Hey, brother, bring a couple of telescopes." And so I bring up 2 telescopes. And so I'm there doing my thing, kind of ignoring him. And he says to me, he goes, "Hey, bro, what's that fuzzy thing up there in the sky?" And I'm like, "What?" He's like, "Yeah, man, I can see it even without the telescope." And I'm like, get out of here, right? And but more profane in real time. And he's like, "Yeah, man." And he had this sincerity in his voice. So I'm like, the only naked eye blob I know is the Andromeda galaxy. And where we're looking, the time of year it is, it ain't Andromeda time. What is this dude talking about? So I'm thinking he's making some kind of error. So I go and look through his eyepiece, and sure enough, there it is. And I'm like, He said he could see it without the naked eye. So I pull away and look along the barrel of the telescope to the sky, and there it is. And then it struck me. I had always known that the Andromeda Galaxy can be seen with the naked eye in a dark enough place, but I knew it had to be really dark, and I hadn't really tried it. I hadn't had the opportunity. But there it was. Now, you can only see the bulge of it, but in the night sky, right, it's bigger than the full moon by several times, right? It's 3 degrees across, right? The moon is like half a degree. That's 6 times bigger. And that thing is 2.5 million light years away. So now again, knowing that I'm looking at something that's 2.5 million light years away, it's looking that big in my night sky, my brain shattered because I could feel how big that thing was. And it was just impossibly huge. And that's the crazy thing about the cosmological realm, right? An atom is 10 to the minus 10 meters across. A nucleus, 10 to the minus 15. That sounds crazy tiny, and it is. But just our galaxy, 10 to the minus 15 going in smallness, 10 to the 21 going in bigness. And I'm just like, bro, man, where am I? What is this cruel joke reality has played on me? You want me to wrap my mind around this bigness? Whoa, man. Wow. Albert Einstein gets a lot of the credit for this idea of space-time, but it originates with Minkowski. And the idea here is that there is a relationship between space and time, but it's more fundamental than I think that we get in our everyday lives we have an understanding for. We know that, there's a relationship between space and time. I can say, I used to live on the Space Coast. Oh, Orlando is this particular distance away, or I can say it's an hour away, right? I can say it in space or time. And we do the same thing using light. Oh, the sun is 93 million miles away, or it's 8.4 or something light seconds away. So space and time, it's intuitive that there is a relationship between it. If I want to describe a line, the length of a line vector in a 2D XY space, right? I'll say, the Pythagorean theorem, a squared plus b squared equals c squared, right? We're familiar with that. When you add that time coordinate, it's not a plus anymore. It turns into a minus. So space and time kind of tug at each other, right? And the consequence of that is that we end up with this idea that you have a speed through space and a speed through time at all times. And just like you have a squared plus b squared equals c squared in the Pythagorean theorem, you have that your speed through space squared plus your speed through time squared equals the speed of light squared. And so you're never at rest in time, are you? Unless you're, because you can never move at the speed of light. So what does this say to us? This says to us that at all times, everything in the universe is moving through space-time because everything is moving through time. And relative to each other, we have speeds, right? If there's only one thing in the universe, what does speed even mean? But if there are two things, now you have, and they're in motion, you have a speed relative to something else. What follows from that is that your speed through space and your speed through time will be different for each one. So each one, by having a different speed through space, has a different speed through time necessarily. And that completely breaks intuition for us humans. Time seems to be something that just ticks along at a regular rate, right? The Earth spins on its axis once a day, goes around the sun on its orbit once a year, right? That's the same. A year is a year, a second is a second, a minute is a minute. Actually not. And it's all because of this 4-dimensional space-time where space and time tug against each other. You are moving through space-time at the speed of light. You're not moving through space at the speed of light. You may be moving through time at near the speed of light, which is the maximal speed, but at all times, you and everything else in the universe are moving through space-time at the speed of light. Not through space at the speed of light, not through time at the speed of light, but through space-time, the combination. It's kind of like Galileo discovered. An object at rest or in motion remains at rest or in motion unless acted upon by an outside force, right? Why is that? Well, at the same way, your motion through space-time is a constant. It is unchanging, but it kind of shifts between space and time. So for example, if you're out there in space all alone, you're going to be moving through time at the maximum speed. But suppose you come next to a gravitating body, like a planet or a star. Your direction through motion will change. So some physicists like to say gravity turns speed through time into speed through space, right? That's why you accelerate near a gravitational body. So, it's difficult to wrap your mind around. It's super easy and it's clear as day in the mathematics of relativity. But, when you are told this and you discover this for the first time, it is a brain breaker. But it also solves mysteries. Like you might wonder, why is the speed of light considered a speed limit in the universe? Well, think about it this way. If I'm at rest relative to you, right? Relative to each other, we are not moving through space. So together, we are moving through time at the speed of light. Now, suppose I start moving rapidly through space. That means I must now move more slowly through time. So in order to move faster through space, I have to borrow. I have to subtract from my speed through time. Well, how much speed through time did I start off with? The speed of light amount, all right? So that's the maximum amount I can borrow. If I bring my speed through space up and my speed through time down, eventually I get all of that speed through time and I'm moving at the speed of light through space. Now, of course, nothing with mass can do that. And at the same time, anything that doesn't have mass, like gravitational waves, light, they must do that. But here's the thing that's really weird. If you look at light with that analogy, right, you have this phenomenon that, the faster things go, the more time gets dilated, right? So the less it travels through time. And not only that, distances shrink. So the faster you go, the shorter distances become. So you would think that light does not experience neither space nor time. But that's not true. That is not the case, right? Why is that? The reason why is, when I say that I move through time at the speed of light, if we're at rest relative to each other, together we move through time at the speed of light, I just invoked the concept known as the rest frame. Well, guess what? Light does not have a rest frame. So you can't make those definitions. It's nonsensical. You can't say light doesn't experience space or time. It doesn't have a rest frame. So, the consequences of moving through space-time at the speed of light and living in a four-dimensional space-time is definitely a brain breaker, but you gotta be careful with the analogies and how you think about it, because there are subtleties all along the way that could lead you to incorrect conclusions. How is the universe both curved and flat? So by flat, we mean no curvature. Well, it's kind of like saying the Earth is both a sphere and not a sphere, right? Or, for my pedantic nerds out there, an oblate spheroid that is somewhat egg-shaped. But here's how that works. You can think of the universe and space-time curvature on two scales. There's the large-scale universe, and then there is the local universe. So yeah, next to planets like the Earth, space-time is curved. Next to the sun, space-time is curved. Next to the galaxy, space-time is curved, right? So I like to think, for example, if you think about our galaxy, we have this giant halo that extends 10 times the Milky Way's radius around it, right? So if you think about the dip in the sheet or the funnel model, that big giant halo of dark matter contains most of the mass. So it's gonna create this deep depression, right? Then you got the concentration of the galactic matter there. There's gonna be another deep depression. And then right in the center, because density matters, you have our supermassive black hole that's like, zoop, right? And so it's like, it's almost like you have a drilling into space-time, because it's all orbiting, right? It's all spinning and orbiting. So locally, there's a lot of curvature and a lot of character to the nature of space-time. But, just like the Earth, it has mountains, it has sinkholes, it has gullies, it has valleys. There's a lot of character to the surface of Earth. But if I step back and look at Earth, it looks like a smooth blue and white ball, right? And the universe is the same way. even though there's all of this local character, if you step out and look back far enough, it looks really smooth. There's a large-scale, global, curvatureless space-time, and there's local, highly curved space-time and curvature of various sizes and intensities based on mass and density and energy and pressure. So this overall space-time behavior takes place in a universe that is not static. The universe is expanding. So when you start talking about the universe at the cosmological scale, you have to take into account curvature of space-time and the expansion of space-time. And that, again, completely breaks our intuition. The only manifestation of space-time curvature that we experience on Earth, we call that gravity. And, we just characterize it with a single number. But in space-time, things are very different. Space is flowing, space is waving, space is stretching. And there is no analogy here in our everyday existence that prepares us for that. And that's why it takes a long time to understand cosmology. Once you get it, it seems kind of simple. But getting your mind around this stuff that is so foreign to us, out there at the cosmological scales, and then you take into effect that there are gravitational effects of phenomena that remains hidden, it really breaks your brain. Quite often when we want to create an analogy for learners to understand how space-time expansion works, we take a sphere and we put lines of latitude and longitude on it. And we place galaxies at the intersections of those lines of latitude and longitude. And then we expand the sphere, all right? So the line segments between the intersections of longitude and latitude, they get longer. But the galaxies themselves still remain at those intersections, right? So space has expanded, but they haven't moved in that particular coordinate system. And that analogy works really well because, the universe is really big. So most of the universe is far away from us. So most of the universe is expanding really fast. So that means that most of the motion of galaxies that we observed is not due to their motion within that coordinate grid, but really it's due to the expansion of the grid itself, right? So we have an idea that we call expansion drag. It's almost like, the faster it's expanding, the more it slows down its intrinsic motion in comparison to that space-time motion. So an example I like to give is tadpoles in a river. So if I'm standing at the riverbank and I'm looking from the edge of the river to the center of the river, what you're going to find is that the water near the river's edge is interacting with the bank. And that makes it move more slowly than the water out at the center. So if I'm looking at some tadpoles right here, I see them moving around relative to the water, right? They're moving back and forth, going back and forth, right? The water, it's kind of like this background in which they exist. But if I look at tadpoles toward the center of the stream, they're carried away down the stream. Of course, they're flipping their little tails and they're moving around relative to some, local coordinate system. But from my perspective, standing on the bank far away, the stream speed is what characterizes their motion. And I would see them as basically at rest relative to the parcel of water that holds them, even though they're flapping around in there. Well, space-time acts the exact same way. Galaxies are moving, right? They're in orbits around each other, they're whizzing around. But because most of them are farther away, it is that motion through space-time that characterizes, that dominates their motion. And so, it's like they're nailed down to that location in space and it's just being carried away by this elevator, right? Or this conveyor belt. So in this expansion scenario, if you go far enough in the distance, you get objects that are moving away from you faster than the speed of light and even faster, right? It breaks our intuition that nothing can move through space-time faster than the speed of light, but stretching is kind of unlimited in terms of how fast it can make things move away from you. But locally, nothing is moving faster than the speed of light. When we talk about the universe as a whole, how does it break our notion of a universal present, right? This is the age of the universe. This is what the universe is right now. Well, man, it breaks it in multiple ways, right? So the first way is we know that the rate at which time travels for every entity in the universe depends on its energy situation, right? How deep of a gravitational well is it in, right? Gravity slows time. So that means when you're in an airplane or in orbit around Earth, that your clock will move faster than someone here on the ground. And also speed matters. The faster you move relative to something else, the slower your clock goes relative to that other entity. So if you look around the universe, the gravitational landscape varies. There are these vast voids between galaxies where there's very little matter. Then you have the so-called web, this filamentary structure where dark matter and matter come together to form what we call the cosmic web. Well, in the cosmic web, time is going to travel more slowly than it does inside these voids. So how do we even have a notion of the age of the universe or now if everywhere has its own clock? Well, it turns out that there are these two things that we can use. One is the evolution of stuff in the universe. Stars are cooking up elements into other elements. So, complexity is arising, right? So you can get different minerals after some time that you couldn't get before that time because they had to be cooked up in a particular sequence to get to exist, right? And the same way, there's light that fills the universe that has a property of averaging out things in the universe. It's called the cosmic microwave background radiation. And so there's a property that light has, right? Light is strongly coupled to space-time. So as space-time expands, light that is traveling through that space-time, it gets its wavelength stretched out by the same amount that space expanded while the light was traveling through it. And so all of the CMB, even if along different directions, lines of sight, the rate of expansion is slightly different, the cosmic microwave background radiation kind of averages out over these nuisance parameters, and so it can serve as a convenient clock. Emergence can serve as a convenient clock. So even though the fundamental reality is there is no universal now, we do have these convenient clocks that give us a bearing, give us a fiducial reference for us to speak in this way. Given this lack of universal now, cosmologists can still talk about the universe at any given time slice because of the cosmological principle, which says the universe is homogeneous and isotropic. That means it's made of the same stuff everywhere, and there are no special locations or orientations or directions, right? The thing about that is that, that homogeneity is homogeneity in space. Everywhere is kind of the same, even though it's not, right? Being in the sun is not the same thing as being on Earth or being in intergalactic space, right? But over large enough averages, we can say it's all made of the same stuff. But every time is unique, right? There is this pattern of emergence that occurs, right? Forces freeze out in the universe. You go from a universe of nothing but plasma to a universe of nothing but gas, and then you get stars and galaxies and structures form. So as you look around the universe, you can say, okay, this has evolved to this degree, so I can attach this time to it. And you also have the cosmic microwave background radiation, whose light is stretching uniformly in all directions, that does give you an average clock. And here's the other thing. When we model the universe when we're doing cosmology, you make these assumptions. You assume that the universe is not lumpy with filaments and all of this. You assume it's a uniform gas. And that allows you to write down equations for conservation of energy for the universe, right? And the acceleration equation for the universe. These equations allow us to perform calculations to look at the past and look at the future. They're very useful. Some people say that astronomy is a science of history because we're always looking in the past. Well, I'd say that, if you're looking at your device in front of you, you're looking into the past. All looking is looking into the past because light has to travel to you. Now, to us, light moves really fast, but that's only because we're so small. The universe is big. Light takes 2.5 million years to get to the nearest galaxy. So light ain't fast as far as the universe is concerned. You have to take that into account when you think about the universe. Is really mind-boggling to know that I can look at the universe as it exists today. I can go a certain distance away from us, and I can look at the universe as it was 100 million years ago, or 300 million years ago, or a billion years ago, or 5 billion years ago, or 10 billion years ago. I can do that because of the time it takes the light to travel to us for us to do those observations. Now, what I can't do is look at myself a million years ago, right? I can't look at the sun a million years ago because that light, I'd have to move faster than the speed of light, travel beyond the light that the sun emitted a million years ago, and then turn around and look at it and say, that's what the sun looked like a million years ago, right? If you had wormholes in science fiction, you could do that sort of thing, but we can't. So, it's one of those limitations of life. I used to play a lot of basketball, and I used to get a lot of basketball injuries. And I used to say to myself, man, imagine if we didn't get injuries, how fun this sport would be. So I just love colliding with people, right? I just love to be physical. Like if I could just run at full speed, just blah, life would be fun. But we have these limitations and we have to live with them. And the speed of light as a speed limit is a limitation we have to live with. And so if you want to understand the universe and how you observe it, and the fact that time and distance are related in that way, is just something you got to live with. One consequence of living in an expanding universe is that there are multiple horizons that define how far away we can see. So the universe is expanding, and the rate at which the universe is expanding varies for every observer with distance. So the farther you go away, everybody in the universe will see the same thing, right? Everybody is at rest relative to themselves. I am at rest relative to myself at all times. No matter how fast I'm moving relative to you, I'm at rest relative to myself. If light is traveling to me from the great distant beyond, right, it's going to arrive at my location based on a relationship between the distance it's traveled and the speed at which it's moving, the speed of light, right? If you're moving at 50 miles per hour, after 1 hour, you will have gone 50 miles, okay? So what does that mean? That means that as time moves forward, light from more and more distant reaches are going to reach me. So if I'm an observer and I'm looking at the limit of my observations, it's going to be a sphere around me that's going to grow with time, right? Just because light from more distant reaches are going to come to me, arrive at my location as time goes on. But now we take into the account the fact that the universe is expanding. And that means that, if I double the distance, things are moving twice as fast, 3 times the distance, 3 times as fast, 100 times the distance, 100 times as fast. Eventually, you're going to get to a point where the expansion rate reaches the speed of light, right? And we define that as the Hubble sphere. So if something is moving away from you at the speed of light and it emits light in your direction, will you be able to see that light? And the answer is, yeah, you will be able to see that light eventually. But there is a point just beyond that where you won't, right? That Hubble sphere also expands with time, but then you get to the cosmic event horizon, where this is the boundary by which objects that emit their light today, anything beyond that distance, their light will never reach us because it will travel through a region of space-time that is moving so rapidly away from us that even as it's trying to come to us, right, that expansion is pulling it back. So if you imagine that you're on a treadmill and the treadmill is moving you away, right? You can imagine a slow treadmill, a faster one, a faster one, a faster one, right? So as a human runner, if you move forward faster than the treadmill pulls you back, you make forward progress. But if you ramp up the speed of that treadmill, eventually you won't be able to make forward progress. And eventually you're going to start getting carried away. And that's how the cosmic event horizon works. Eventually you get to a point where space-time is expanding away from you so fast that whatever light you emit today, it's never going to make it to you. But notice I say light emitted today. If you look at the most distant objects whose light is reaching us today, they were much closer to us in the distant past. And that's when their light started traveling to us. But then the expansion of space-time took them beyond our cosmic event horizon. So those objects, even though their light is coming to us and will eventually reach us, the objects themselves are beyond the cosmic event horizon. And so that defines a third horizon called the particle horizon. It's not for objects who's emitting light today. It's for objects whose light is arriving at us today. And so those objects, if you look at the cosmic event horizon, it's around 16 billion light years away. The Hubble sphere is around 14 billion light years away. The particle horizon is more like 46 billion light years away. So we can see the light from objects that are now 46 billion light years away from us. That expanding universe changes everything. In the far future, which is, far is relative, as far as the age of the universe, as we can extrapolate it, the universe is going to be around for a very, very long time. So as far as I'm concerned, we're still in our universe's infancy. If I look at how long the universe is thought to exist, is going to exist, with stars in it, for example, and I say, okay, let's make the analogy that universe existing into the future known quantity is equivalent to a human being that's 100 years old. How old is the universe now in comparison to that? It's like a couple of days, 2-3 days old right now, right? So the universe is still at its infancy. And one thing that I like to say is, how the universe is still at its infancy? Because you can observe it. Only a new universe is observable, because that expansion is going to take all the galaxies, except for the ones that are gravitationally bound to us, like Andromeda, outside of our cosmic event horizon. And eventually we won't be able to see any of them in the distant future. And the Andromeda galaxy and the Milky Way galaxy are going to combine, right? They're going to collide and combine to form the Hakeem galaxy, or, Milkomeda. And at that point, our entire observable universe is going to consist of this galaxy and these cosmic backgrounds. Everything else will be swept out of our line of sight. We can still make measurements. We can use like pulsars to measure gravitational waves that are passing through this universe and do some cosmology. We can still measure the cosmic microwave background radiation, its polarizations, its fluctuations and variations, and do some cosmology. But as far as looking at galaxies, that game's over.
Chapter 3. The two multiverses we might live in.
What do physicists mean when they say a multiverse? It is derived from what we mean when we say a universe. And a universe has characteristics. And one characteristic is sort of like defining a living cell, right? The thing that defines a living cell is that it contains a volume that encloses it and separates it from the rest of existence. So a universe is that. It's a volume separate from the rest of other existences. And inside that universe, there are specific physical constants that characterize the physics within that universe and the interactions within that universe. Things like the gravitational constant, the action constants that we call Planck's constant, or the constant that combines energy and temperature that we call the Boltzmann constant, right? Then there are some other more obscure constants in there, like the fine structure constant. But these constants, these values, we don't derive them. They just are, right? And so every universe will have its own set of constants that define how physics takes place within that universe, and it will be a volume cut off from the rest of other such volumes. What is the problem that the many worlds interpretation of quantum mechanics is trying to solve? It's trying to solve what we call the measurement problem. And the idea that, when we make a quantum measurement, that vector that describes the state of the system goes from being expressed as a sum of the possible states of the system, right? When it's measured, it will only be found in one state. But in the pre-measurement state of the state, we describe it as being a combination of all the possible states. But once you make a measurement, it's always found to be only in one of the possible states. So what's going on there? In the first instance, in the initial state, you have a state vector that's made up of all these sums. And then after measurement, the state vector just ends up having one component of that sum. So what does that transition look like? Well, is the measurement changing the state of the system in this way? And some physicists, what they call the Copenhagen interpretation, say, yeah, the system collapses into that one state upon measuring. But some other physicists came up with a different idea. And they said what's happening here is that every state actually exists. And every state kind of corresponds to its own universe. So the measurement that you get tells you which universe you're in, right? So all of the possibilities, all of the possible states occur at every measurement, but they just occur in different universes, which means that there are different copies of everything in our universe. Every time a measurement is made, you're popping off these new universes. You know, it's weird. It's very, very weird and strange. It seems counterintuitive. It seems to go against conservation of energy. And the other thing is, we don't even really define what it means to make a measurement, right? Is it just an interaction? So for example, if I have a photon and an electron interacting, right? An X-ray that is traveling towards some atom. That atom has an electron. So there's a famous experiment in physics known as the Compton scattering experiment. And this is the experiment that shows a particle property of light, that it exchanges momentum the way particles do, like billiard balls colliding. So in that interaction, before the interaction, both the electron and the light are described as waves, but in the interaction, they both behave as particles, right? So does that interaction create a new universe where each goes from a superposition state into a definite state? So think about that. Many galaxy clusters are full of this hot X-ray emitting gas. And all these galaxies, which contain gazillions upon unfathomable numbers of electrons, are orbiting within that hot million-degree gas. They're being bombarded by X-rays. Is every interaction spinning off a universe, right? It's nuts. And even then, you know, when you talk about the fact that that state vector in the pre-measurement state, that wave function in the pre-measurement state has probabilities built within it, what does the probability of a measurement even mean if every measurement has a probability of 1, right? Every measurement has a probability of certain in some universe. So what do these probabilities even mean? Some people think, you know, on the fringes that might be real. And some, you know, because they think that that idea of the wave function collapsing is too unphysical. So there must be some other explanation. And this is one of those interpretations. And I find both explanations to be, okay, I think we're missing something. I think there's something going on that we're not quite interpreting right, we're not understanding right. And, you know, I love to live in mystery. I love ignorance, right? Once you know you're ignorant, you can fix it. you can, you know, it's a provocation. You can design an experiment. You can design a thought experiment. You can design mathematics to get to the bottom of it. And I think that this problem has young, curious people and old, curious people doing exactly that. But if you accept one or the other, you think you got it solved. Now, suppose, you know, we can speculate. The thing about having a human mind is you can imagine things that have never been observed, that, you know, may never be observed, can maybe never exist. But you can imagine them. You can imagine a universe in which the many worlds interpretation holds up to some sort of experimental scrutiny. And we're like, oh my goodness, it's real. What does that mean for our reality? Does that mean that now we have the possibility of accessing those other universes? Well, what you find that happens is a new sort of insight into nature is kind of like a new technology, right? The internet created a whole new economy. Then smartphones on top of the internet created a whole new economy. So whenever you have these new ideas like string theory, right? It didn't work out for physics, but mathematically, it created whole new areas of exploration, right? A very rich area of mathematical understanding and exploration. So the first thing is you don't know what you don't know. So if you find that this multiverse idea of many worlds interpretation turns out to be true, does that mean that we're forever isolated from these other universes and can never access them? That is the current way that most physicists think that, yeah, if this were true, that would be the case. But if it turned out to be true, people are really going to start thinking about things differently. And in that exploration, some clever group of researchers may very well find ways of interacting between universes, right? They can come up with experiments that, say, oh, there was once this idea that gravity is so much weaker than all the other forces because it leaks out into this parallel universe. And what we see as dark matter in our universe is a gravitational pull of matter in a nearby parallel universe. And they came with an experimental idea. Well, if you could measure gravity at a short enough distance, then what would happen is you'll see suddenly this increase because that's before it has leaked out into the other parallel universe. It was never measured, but the point is that they came up with a way to measure it. And I think that if we do evolve to a state of finding that, yeah, there's something to this, we're not going to stop there. We're going to keep exploring, and who knows where that's going to lead. Another way physics invokes the idea of multiverse is in cosmology. And this came about via a mechanism that was hypothesized to solve a couple of problems in cosmology that researchers began to notice in the late 20th century. And those problems are called the flatness problem and the horizon problem. And the solution is something called inflation. And inflation is this notion that at very, very early time, in the very earliest moments of our universe, the universe doubled in size over and over and over and over again in a tiniest, 10 to the minus some double-digit number of seconds, right? A billionth of a billionth of a billionth of a billionth of a second, something like that. And the consequence of that is that today, regions in the universe that appear that there would have been outside of each other's cosmic event horizon back in those times and could have never communicated with each other, could have never exchanged energy with each other. When we observe those regions today, they appear to have the same temperature, as if they were in contact, right? So if I look at the cosmic microwave background radiation coming from that direction and compare it to the radiation coming from that direction, it's roughly indicative of the universe being at the same temperature. How could that possibly be? That should only, if you do the calculation, assuming a standard hot Big Bang model, it's only about twice the size of the full moon regions that should have about the same temperature, right? But, it's the same temperature across the entire sky. What that means is regions of the universe that today appear as if they were forever outside of each other's horizons were at one point within each other's horizons, and that rapid expansion of the universe took them so far away that they have that appearance today. So what do I mean by horizon, right? So in relativity, every future possibility is bounded by the speed of light, all right? So if you move at the speed of light, there's what you can reach, and you can't reach anything beyond that, right? So you have what is known as a future light cone. So if you look at the future light cones of all the regions of the early universe, if we take those regions today and you go backwards, they would appear to be outside of each other's light cones. But clearly they were inside of each other's light cones. And this inflationary event is what allows that to manifest in a physical way. But then you need a reason for it. How could that have happened? When we started studying how that could happen, that led directly to the idea of multiverses being real. In the cosmological realm, the types of universes that exist in the multiverse are fundamentally different than the ones we see in the many worlds interpretation. So what that means is, you could think of it like baking a loaf of bread, right? You bake the loaf of bread, the bread expands. And inside that bread, there are little bubbles of air pockets, right? So every air pocket has its own history, and yet the bread itself has its own history. And every bubble is separate from every other bubble. So they have their own separate histories. So that's similar to what an inflationary universe would create. But the difference is that the main background, the whole loaf, that universe, right? That thing is there, it's expanding super rapidly, it's doing its thing. And when it pops off bubbles, it doesn't pop them off at the same time, right? These bubbles where they go out of this inflationary state and then nucleate into a new universe, they pop off right, one happens here. If another one was to happen very near it, because that bigger space is expanding so rapidly, it will be so far away by the time it nucleates out that these bubbles are forever separate from each other. If the multiverse of the cosmological realm that is generated by this process called eternal inflation is true, then there are multiple spacetimes. There is the bulk spacetime, and I don't want to use that word bulk because there was this old model of brains and bulks, right? But truly, there is a bigger spacetime out there. And every universe has its own spacetime with its own history that evolves separately from that bigger space-time once that bigger space-time, births it. The properties in each bubble universe will be slightly different. Each have its own history. Each have its own space-time curvature. I am so impressed with this animal on Earth that we call Homo sapiens, right? Not long ago, you were eating the leftovers of predators on the plains of Africa. At a certain point, you decide you're gonna break rocks and turn them into tools. And you go from that to melting sand and turn it into quantum technology and performing experiments and understanding that we live in a universe that is evolving. And you make measurements of this light left over from the origin of the universe called the cosmic microwave background radiation. And your physics tells you that, hey, it should have fluctuations of every sort. And if this multiverse thing is real, then there should be this thing called a super horizon fluctuation. And you make this careful measurement, you get to the point where you send up the Planck satellite, and there it is, clean as day, the signal of the super horizon fluctuations. And you say, wow, eternal inflation looks like it's real and looks like we are in a universe. So we have reached the point of experimental verification of the multiverse, but that is a big claim. So it is not a conclusive piece of evidence, but it is a strongly circumstantial piece of evidence. Some physicists do say it's conclusive. Some physicists that I respect greatly say that it's, for their thinking, right, it's conclusive. I'm not convinced that it's conclusive because I don't quite understand it all yet. But I'm working on it in the midst of everything else I'm working on. So, we've reached that experimental point. And, man, what a fascinating place nature and existence is. What we see in physics over and over is that stuff pops out of the equations that leads us to new discoveries, right? Maxwell discovering that light is an electromagnetic wave by manipulating the so-called Maxwell equations. But, more often than not, stuff pops out of the equations that just isn't true. And you got to find some way of saying, oh, here's how we use that, right? It turns out this part of the equation is reality. That part of the equation is just mathematical junk that's left over. At the same time, though, we have people like Albert Einstein that comes around. And he writes down equations for, say, general relativity, and it creates phenomena like black holes and gravitational waves that won't be measurable for decades to come, if not a century to come, right? So there are things that our equations predict that may be just complete nonsense, and there are other things that may be insights into the universe, but we have no way of measuring them now because we just haven't developed to that level of technology yet. What that tells me is we need to take these predictions seriously. And we need to continue to, as a society, fund people to pursue these questions. Because every time we find out some new fundamental nature of reality, it leads to new engineering that allows us to take advantage of this stuff. Research at the edges, research into these avant-garde ideas is the fertile ground for discovery. And that is where we must explore. Don't just dismiss it as that can't be true. The universe has never cared what you think can be true. It is up to us to listen to the universe and ask the universe, hey, universe, what are you? And our observations and our calculations are the way that the universe answers those questions when we ask.
Want to support the channel? Join the Big Think members community where you get access to videos early, ad-free.